All right. Well, as you might expect by now, we are dealing with a lot of stuff, in particular with regards to setting up these transformation rules and how Galilean and the Lorentz transformations differ, all that kind of fun stuff. However, there is a nice way of writing all of these using matrices and column vectors, and unfortunately, you might not like it, but this is the way of it, and we will compact it. And you'll see it used in the later sections heavily, so let's dive in. The statement reads, for part A, write out the matrix that describes a Galilean transformation, or equation 12.12. Part B, write out the matrix describing the Lorentz transformation along the y-axis. Note that we previously had been doing it along the x-axis. C, find the matrix describing a Lorentz transformation with velocity v along the x-axis, followed by a Lorentz transformation with velocity v bar along the y-axis. Does it matter in which order the transformations are carried out? If you've had any background in linear algebra, you're already sniffing out some things that will be determined here. So let's go talk about them. All right, so in part A, what we notice is that we have the transformation rules guided by the Galilean transformation, where we just have the kinematic expressions here. So x bar is x minus vt, no gamma factor. We have y bar, y, z bar, z, t bar, t. Easy enough. We like that. So if we set things up where we have c t bar, this is our normal 4-vector kind of isolation where we have the 0th component is t bar, or the t component, and then we have the spatial components. What we could say is that this transformation rules, where we multiply c to t bar and t, well, this is equal to some matrix multiplied by the column vector ct, x, y, and z. And if you remember, matrix multiplication tells us that we have the row of the matrix before it gets multiplied into the column vector of the matrix after it. So first row to the column gives us the first entry. So we're simply saying that a 1 times ct gives us ct bar, and that's accurate. Cancel the c's on both sides. Check. Beta here is equal to v over c. So we need a negative beta, a 1, and a 0 in the second row here, because taking this, multiplying into this, gives us negative beta times ct plus 1 times x, and then all these components are 0. And we see that negative beta times ct, the c's cancel, and we're left with negative vt. And in here, we have negative vt. And then we have plus x, so we have the x there, so check. And, notice that our main diagonal just gives us back the coordinates that we want. But yeah, with these matrices, they're really easy to deal with once you get them set up, but it's going to take a little work for you to get familiar with them. Now, what we can do is check by multiplying this into the column vector. Kind of just did that out loud, but here's the written work. We have the c's canceling on the bar and t terms, so we're good there. We see that we have the written out form, so I'm just going to leave that there and let you check the rest if you want. But, matrix multiplication does matter with the respect to what goes first and second, and we always have to do row to column. All right. So the more compatible one that we actually want and we actually need is the Lorentz transformation along y. Note here that we normally put it along x, but here we're moving along y, so y gets the gamma factor with the Lorentz contraction, and similarly time just stays with the time dilation, except we're moving into y, so this goes to y instead of x. That being said, set up the matrix in the same respectable way. Here we have the time, spatial, spatial, spatial. Again, our main diagonal tells us that we need a gamma on the time and the y component. So that checks, and then everything else, the x bar should just be left alone. since we're not contracting in that direction. Z bars are left alone since we're not. And now it's just a matter of putting the gamma betas in the right spots. Again, gamma is the Lorentz contraction, and we have beta equal V over C. So be careful of that and let everything else run through. And yeah, as you see here, when we multiply it out, everything checks back, so we're good. And we call this matrix specifically the Lorentz transformation matrix, and we use a capital lambda for that. So if you like general relativity, you've seen capital lambdas before in the equations. This is what you have to do, and it's you have to be careful in which direction you are moving. All right, so moving on then. Part C, we have, since the transformation is along the x first and then the y, we need to apply the x transformation first and then the y. Okay, what this tells us is that if we want the total transform coordinates f bar, we have to multiply by the transformation matrix x and then multiply by the transformation matrix y. But this is the same as f bar if we had just multiplied the two transformation matrices, but again, x first, then y. Okay, the reason why is because we're left with this thing here. So the barred coordinates, or the transformed coordinates, this is the y transformation, this is the x transformation, and these are the coordinates that we're trying to transform. So we have to multiply this into this, this into this. That gives us another column vector. And then we multiply this transformation into this one. The reason why we have to do that is because we see that we have lambda equal lambda, total lambda equal lambda y lambda x, as stated here. And if we distribute this row into this column, this row into this column, this row into this column, and so on, we get the total transformation matrix, which is huge. And again, if you've ever taken a linear algebra class, you know that matrix multiplication is in general not commutative, so we have to go in order. So with that, welcome to the transformation, or welcome to the matrix formulation of these transformation rules, and we will definitely see this again.